Appreciate you guys joining us today. We're going to be talking about a very important topic as it applies to machine learning and deep learning, and that is explainability or interpretability. This is one of the central challenges of deep learning. It's pretty critical to the widespread adoption of AI, and it's something you'll hear about quite a bit in the popular media. You'll often hear that AI is a black box, and we have to, crack open this black box so as to assuage non-technical folk and business people and politicians and so forth. We ourselves work across a variety of verticals where this is an issue. We work in the automotive space, aerospace, industrial, and probably the best example I can give you where the need for explainability was quite acute was with one of our autonomous vehicle clients that ran into a very strange situation where their car would turn left with increasing statistical frequency when the color of the sky was a certain shade of purple, right? And of course, you guys know that the color of the sky should not influence the way a car turns. And after much debugging, we had discovered that they had done the training for this particular turning scenario in the Nevada desert when the color of the sky was this particular shade of purple, and that was the correlation that the network had made, right? And it's an important reminder that neural networks and deep learning and machine learning, they are modeling not the real world, but the data that you present them. So it's very important that we unwind this so as to understand what we call nonsensical correlations, so these boundary cases do not find themselves into production. So how do we actually crack this problem? Well, one of the main ways our industry has purported to do that is by means of explainability algorithms themselves. And when I was thinking about this, if you think about what an explainability algorithm is purporting to do, it's not too dissimilar from subatomic or particle physics. Some of you might recognize these patterns. These were patterns from the LHC when we discovered the Higgs boson in 2012. And what's fascinating about this realm of physics is that you never make direct observation of something. All you can say is that statistically, with a certain level of confidence, that you are quite certain that the reality that you have purported to occur has in fact occurred. And when we think about what explainability algorithms are trying to do, they are trying to tell you with some certain probability that this is the reason why the neural network made a certain decision. Now, one of the challenges with doing so is that there doesn't appear to be a lot of standards around these explainability algorithms. In other words, if the explainability algorithm itself is the byproduct of artificial intelligence, how do you know that the explanation you are putting forth is in fact valid? So our team authored a pretty seminal paper. It'll be presented at NeurIPS later in December in Vancouver. And we are, in effect, proposing a standard model for explainability algorithms. So with that, I'll invite my colleague, Michael St. Jules, up. He's one of the authors of the paper, and he's going to get into the technical details of what we're proposing and what the results were. So, Michael, please take it away.
What should explainability mean in more concrete terms? So for us, for this talk, we're looking at critical factors. So these are the subset of features of a given input for the neural network that are deemed most important for the model's actual prediction on that input. As you can see in these two images of iPods, in the second image, we have the critical factors highlighted. And in the third picture, we have the probabilities or the confidences in each class. So originally, it was very confident that the image was of iPods. But when you remove these two critical factors, or three, I guess, it thinks it's a sweatshirt, right? So more commonly, however, explainability algorithms output saliency maps. So these are heat maps. So for each feature, there's a value associated with the feature representing how important that feature is. And that can be done on a per class basis. So for each feature, for each class, there's a value. But more generally, we want to think in counterfactual terms. So what would have happened if it weren't for these features, right? So given that we have an idea of what explainability should mean more concretely, should we trust these algorithms? Well, not yet. There are several algorithms defined in counterfactual terms, which is good. But there are issues that remain, like efficiency, or trade-offs between efficiency and accuracy, robustness, and also selecting appropriate counterfactuals in the first place. And furthermore, we rely a lot on human verification, which is both time-consuming and subjective. So we propose as a solution to this reliance on human verification metrics. So we'll define the quality of an explanation quantitatively, and this allows us to compare the quality of explanations between algorithms and also can guide the design of new algorithms. So before I get to our work, I'll do a brief overview of some existing work. So an older paper defined the area over the perturbation curve, which is effectively the average of the difference between the output of the model on the original input and the output of the model on the input with the top k features replaced. So where top k is defined in terms of the saliency map. More recently, in this recent paper, the authors measured how often the removal of regions identified as most important changed the predicted class for the algorithm integrated gradients. And they also did this with and without adversarial patches. So most important for them, again, was defined in terms of the saliency map. And the metric, one of the metrics we defined captures this generally. We'll call it strict impact score. So with this in place, we need to get to a bit of notation to start. Given a neural network N, its input X, it should output a decision and a confidence in that decision. For classification, the decision could just be the predicted class, and the confidence would be the softmax value associated with that class. And then we can look at the output of an explainability method on that input X and the neural network. So this should be a subset of the input features that are the most important according to that method. And then we can look at that original input without those features, those critical factors. We remove them, and in our case, we're setting them to 0. And then we can look at the output of the neural network on that modified input. So with this notation down, we consider 2 types of impact. The first is decision level impact. That's when the decision changes after the critical factors are removed. And confidence level impact, in which case the confidence in the decision drops significantly by a constant factor after the critical factors are removed. And so we defined impact score and strict impact score in these terms. First, strict impact score is just the relative frequency with which there's a decision level impact, or the relative frequency with which the decision changes without the critical factors. And the impact score is the same, but we also consider confidence level impacts on top of the decision level impacts. So one word of caution, of course, is that these metrics don't consider the sizes of the critical factors. So of course, you could just have your explainability algorithm output all the features. And that would look pretty good on both of these metrics. So this is another consideration that you should take with these at the same time, or some other measure of relevance. So another metric we defined was impact coverage. And this is a specific use case that we have experiment with. It's when we have an adversarial patch applied to an image. So that's depicted in the second image here. So the adversarial patch, it's designed to change the output of a neural network when it's applied to that image, or the decision. So in this case, the image was originally predicted to be an iPod, and then once that patch was applied, the network thought it was a monitor, right? So adversarial patches are designed generally to have this kind of behavior. So we think that an explainability algorithm, if you give it an input that has an adversarial patch applied already, it should give you back that patch. We think that that's what's important for the decision. So we want to measure the degree of overlap between the critical factors output by the explainability algorithm and the adversarial patch itself. So we define the impact coverage as the mean intersection over union between the adversarial patch and the critical factors. So with this, we can get to some experiments. The network and data were just ResNet 50, trained on a 50 class subset of ImageNet. The explainability algorithms we tested were LIME, SHAP, specifically the deep lift variant, expected gradients, and our own algorithm, GS-Inquire. I should add that the comparisons are fairest between SHAP and expected gradients, and then between LIME and GS-Inquire. For SHAP and expected gradients, we define the critical factors for a prediction from the algorithm's saliency map arbitrarily as the top 25% of features according to that saliency map, specifically the class-specific saliency map for the predicted class. So this guarantees that the sizes of the critical factors, well, it's 25% of the image, right? Constant. For LIME, the critical factors are just the superpixels with positive weights for the prediction. It's a linear model. And for our algorithm, well, it produces critical factors by design. OK, so our first experiment, you can see in these images here, these are the critical factors identified by each algorithm on 2 different images. You can see the impact of the removal of these critical factors. And we calculated both the impact score and the strict impact score. So looking at these, SHAP and expected gradients perform roughly the same. Expected gradients had a slight advantage. GS-Inquire seemed to have some advantage over LIME. But again, we didn't look too closely at the differences in sizes. So that would be something to look further into. And then our second experiment was with the adversarial patches applied to the images. So we tried adversarial patches of various scales. You can see going down, patches get bigger and bigger. And we calculated the impact coverage. So in this case, all of the scores are pretty low, especially for LIME. So this might tell you that either all of the algorithms are bad, or our assumption in defining impact coverage was inaccurate. So maybe things outside of the adversarial patch do matter, or maybe the adversarial patch, not the whole thing is important, just parts of the adversarial patch are important. And in particular with LIME, because it's defined in terms of superpixels, you can see, well, I guess you probably can't see, but there are a few pixels highlighted inside the adversarial patch at the bottom. So the issue seems to be that it's selecting very, very small critical factors. And that's why the IOU or impact coverage is so low. So we also looked at the impact scores on the same problem with the adversarial patches applied. And you see the same trend as last time. Similar across all scales, expected gradients, and SHAP were, again, fairly similar, SHAP a bit better. And LIME, as with the impact coverage, it did pretty poorly again. So this is basically the extent of, this is what we covered in our paper. Future directions are considering different problems, like natural language processing, different types of adversarial attacks, say like 1 pixel adversarial attacks, see if we can identify that single pixel, and improvements to the metrics and other metrics.
Okay. Thank you very much for the talk. I guess I had 2 questions that came about. One, when you were measuring sort of impact, you were setting the variable or the one feature to 0 in your example, which I guess was a proxy for trying to remove the information that feature was giving the system. Mm-hmm. Were you concerned, or did you look in at all as to whether or not 0 was a reasonable value for that feature? So it's possible that it would be impossible in practice, in real data, for that. And I know for images that's not necessarily the case, but for arbitrary data, for that thing to be 0. And so you might be ending up in a situation that isn't representative of what your model will do. And then sort of tagging on to that, are you worried that in complex nonlinear systems, setting it to a single value like that only shows you the type of explainability and the type of learnings you have for a subset of the queries? And how would you think of combating that?
Yeah, that's a fair concern. Setting it to 0 was like our first attempt. there are lots of like different approaches to like fill in these values, like in painting or random values. All of them have like some drawbacks. I think we might have seen one example where there is a critical factor. Its shape was kind of like sunglasses. And that if we set it to 0, it actually thought the image had sunglasses in it. So this is a mistake, right? And this is actually going to be like a problem going forward in defining like impact score, these kinds of metrics, like what kind of counterfactuals are reasonable to use. And I think this is going to be a hard problem to solve. I'm not sure exactly what direction it's going to go in.
Sorry. The other question is, you focused a lot on looking at features or elements of data that are given to your model. Have you looked at all trying to see how the model's biased on features that are not given to it? And what I mean here is, and again, pictures might be a bad example, but if I build a model on, say, hot topics in the States, things like mortgage defaults, right? What we've seen with models in the past, and there have been scandals around prejudices around racial lines, even though the model may not have been given the explicit ethnicity of the intended borrower, we saw biases because of the training data and a bunch of other sort of sub-factors. Have you looked at all as to how to sort of do explainability around things that, or how to account for biases around things that may not have been given as explicit feature inputs?
Yeah, so I guess one way to think, so specifically in this case, we're looking at images, so this is not much of a concern, but yeah, I guess generally, you would think that, like if it's tabular data, then you can vary the value in that position. So you could replace it with something that, like you could replace demographic information that would go into the counterfactual. And if we're modeling it as like the impact score as actually changing, replacing the input features, then we could actually input that missing data, right? The data that's not given, and then we look at that impact too. And in particular, in some of these algorithms, like they're saliency maps, so they just give you like the top, like you can calculate the top X% of features from these, and some of these could actually be like negative features. The fact that something wasn't there could count. For something like Lime, it's a linear model. Some of the weights are negative, right? So the absence of a feature could count positively towards a specific classification.
Hey, so I have a question that's quite similar. Well, it's tangential to that. So in the case similarly of non-image, non-text data, so as an example, capital markets, right? You want to make some decision based on every single thing related to a company. So this is the work I do, so I'm just giving that as an example, right? And so let's say I have 1,000 companies. I have every single little piece of information from a specific database. And I think, I have a hypothesis that a new data point might be important. And in my real example, so I want to use, let's say, the demographics of the C-level of all these companies. So it's very expensive. I can't get them. I can't get it at all. So I'm thinking of a use case where this might be applied. I can say, get a sample from my data set, collect these, let's say, data points for this demographics, then see what this would look like without or with this information and see if I should go pay the thousands of dollars for the access. So would that be a use case for this?
I guess that's more looking at the impact on the actual model itself. Like you would have an idea of accuracy. You want to see generalization of your model, see if it's more accurate with or without this data. The explainability algorithm will only really tell you whether it's kind of like looking at the right things or not. So if you have like some type of information that's not in any of your data, then the explainability algorithm probably wouldn't tell you anything about that.
So you would need, let's say, so then I would have all of this information, and then I can use explainability algorithm to see if my money was worth it or not.
Yeah, you could. Yeah, after the fact, you could do like a small subsample. Well, I mean, you do need to train you do need to train the network, so you do need a decent size.
And it's not 1,000; it's dozens. So yeah.
Yeah.
Right,
so.
yeah.
So I wonder if you can speak at a very high level about some of the, I don't know, apparent controversy there is around this question of explainability. So for example, just a few minutes ago at the end of a previous talk, the speaker expressed a very strong, clear opinion about basically calling into question the whole notion of explainability, that there are other ways to justify using AI. And, and I guess that's, maybe my question is more around just what should we think when we think of these terms? I think there's one that I don't hear very often, which would be something like a justification, which I think maybe some people are actually thinking of when they hear about explainability or when they speak about explainability. Okay. And I guess also, why is it coming up now so intensely? I mean, I know the answer to this, but still, given that we've long had complex algorithms that have nothing to do with AI, that haven't really, until very recently, generated this demand for explainability. So really, I don't have a specific question, but just a high-level explanation to put all of this explainability stuff in context.
Yeah, well, I'll take a stab at that if I can. So I tried to follow an experiment with my wife at dinner 2 months ago. So we went to dinner. We have a 1-month-old son. Sorry, a 1-year-old son. Feels like he's a month. And she ordered salmon at dinner. And I said, why did you order salmon? I was trying to test her explainability. And she said, I ordered salmon because I felt like fish. And I said, well, why'd you order salmon and not tuna? I just felt like salmon. Why did you just feel like salmon? I just felt like it, and then I ruined dinner. But you raise a very good point. Are we holding AI to a higher standard of interpretability than we are with ourselves? And what I would say is, because of the ubiquity of these systems, it really gets to a question almost of justice and responsibility. So if there's a crash and a driver hurts somebody, we're prepared to deal with that person being responsible. I think the question partially on a societal level of explainability coming up is we won't accept that there's a black box and we don't have any insight into what happened. So that's like a generalized answer. I think though, technically, and we have many technical people in the room, when we approach the question of explainability at the level of detail that our team did this paper, we're trying to assist engineers and deep learning developers to understand the holes in their models before they put them into the real world, right? And so there's two very different levels of explainability almost. There's a level of an engineer or a data scientist saying, what are the shortcomings in the model that I can identify ahead of time? And then there's the question of, to person, why did you reject my mortgage application? And we need to work on this first more technical and granular problem before we can escalate to the second. That's what I would say.
So your model seems to, or your work seems to rely on the existence of these adversarial patches. Do you have any thoughts about sort of if there's different adversarial patches, if that affects the scores, or do you have any ways to generate your own adversarial patches if they don't already exist?
Like for now, we just started with a known approach. I mean, we're going to look into different approaches, but this is what we've done so far. Like as I said, one pixel attacks would be interesting. That's not, I guess it's not an adversarial patch, but